Hi, and welcome to the brief introduction to the concept of hardware-software co-design lecture. My name is Majid, and I will be your guide throughout this tutorial. In this lecture, we will discuss the co-design concept and then focus on one core topic, which is the design space exploration. This lecture is divided into three main parts. The first part will introduce the basic definitions of the hardware-software co-design concept and the purpose of such a concept. We will then talk about the past and present of the co-design in a travel through history from birth to present. Part 2 of the lecture will discuss the core topics of the design space exploration. We will start off by discussing the driving factors in the co-design realm, then the advantages and disadvantages of the co-design space between the hardware and the software. Finally, we will touch briefly on the advances in the design space exploration, specifically in the on-chip architectures. To conclude, part 3 of the lecture will discuss the future of the co-design and put the final remarks to this lecture. Now let's get started. Hardware-software co-design emerged basically as a new discipline to design complex integrated circuits, also known as ICs, in the early 1990s. Hardware-software co-design is a broad term to capture many different things in the electronic system design. This is by no means a universal definition, but it will help put readers from different backgrounds on the same line. In this lecture, the hardware is modeled in a single clock synchronous digital circuits, usually in combinational logics and flip-flops. Examples would be registers, adders, and multiplexers. Cycle-based hardware is usually referred to register transfer level, also known as RTL, because the behavior of the circuit can be thought of as a sequence of transfers between registers with logic and arithmetic operations performed on signals during transfers. The signal clock model is a very convenient way. The single clock synchronous model cannot express every possible hardware circuit. For example, it cannot module events at a time resolution smaller than a clock cycle. Thus, some hardware cannot be captured using single synchronous model, for example, in asynchronous hardware and dynamic logic. For the software part, the low-level construction details of software are important because they directly affect the performance and the implementation cost. These techniques can be controlled using programming languages, for example, C. Software has important application in the software-hardware interface, as it organizes variables into memories and techniques to control this form. However, it is important to know that some optimization can only be handled on the hardware-software co-design at the level of assembly coding. The co-design part, which is the hardware-software design of cooperating hardware components and software components in a single design effort. In reality, there is many forms of hardware software, and some of the examples of co-design are FPGA, which is a hardware circuit that can be configured to a user-specified netlist of digital gates. The program for an FPGA is a bit stream, and it's used to configure the netlist topology. A soft core is a processor implemented in the bit stream of an FPGA. However, the soft core itself can execute a C program as well. DSP, also known as Digital Signal Processor, is a processor with a specialized instruction set optimized for signal processing applications. An application-specific instruction set processor, ASIP, is a processor with a customizable instruction set. The hardware of such a processor can be extended, and these hardware extensions can be encapsulated as new instructions for the processor. The cell processor used in PlayStation 3 contains one control processor and 8 slave processors interconnected through a high-speed on-chip network. The software for a cell is a set of 9 concurrent communication programs, along with configuration instructions for the on-chip network. These examples illustrate a few of the many forms of hardware and software that designers use today. The common characteristic of all these examples is that creating the software requires intimate familiarity with the hardware. We can summarize that the hardware-software co-design is the partitioning and design of an application in terms of fixed and flexible components, where the fixed components are the hardware components and the flexible components are the software components. Now, before delving into technical topics, the major purposes and intentions of hardware-software co-design are summarized below. These are explained by looking at different interpretation of the syllable co of the word co-design: coordination, concurrency, correctness, complexity. Coordination. Coordination is a co-design technique which is used today to coordinate the design steps of interdisciplinary design groups, including firmware, operating system, and application developers on the software side, as well as hardware developers and chip designers on the other side to work together in all parts of a system. Concurrency, which is the tight time to market windows, force hardware and software developers to work concurrently instead of starting the firmware and software development as well as their test only after the hardware platform is available. It can be seen that Codesign has provided an enormous progress to avoid the bottleneck by either starting from an executable specification and then applying the concept of virtual platforms and virtual prototyping in order to run the concurrently developed software on a simulation model of the platform already at a very early stage. Correctness, needless to say, is the correctness challenges of complex hardware and software require techniques to not only verify the correctness of each individual subsystem, but also co-verify their correct interactions after their integration. Complexity, of course, is the co-design technique which mainly drives the complexity of today's electronic system designs, and serve as its means, or the least way, is to close the well-known design gap to produce correctly working and highly optimized system implementation, in respect to cost, power, and performance. In this section, we will travel through history to understand where did the co-design start from, its progression stages, and where we are today. The evolution of co-design is summarized starting as an emerging discipline in the early 1990s to a mainstream engineering technology in its second generation. This slide will cover only the major research themes addressed in each decade of research by only highlighting some important approaches. It is important to note that the discovery and subsequent boom of co-design in the complex electronic systems started as early as the 1980s. In the initial work by Prakash and Parker, a co-synthesis problem was formulated as a mixed integer linear program which simultaneously determined a multiprocessor topology as well as a schedule and allocation of tasks onto an architecture. Since then, the problem of automatically partitioning tasks or processes into hardware and software was soon recognized as an increasingly important research topic, with the advent of forming a research community starting in 1992. Co-design took place in Grasso, Germany, under this name or simply Codes. Major subsequent events dedicated to this new research fields were then organized in Colorado in 1992, Cambridge in 1993, France 1994. The event was simply called Codes and organized in other places later in Germany, Seattle, and Rome. It also continued to flow in Italy, San Diego, Denmark, Estes Park, and finally in 2003, Codes became the International Conference on Hardware-Software Co-Design and System Synthesis, as a merger with the IEEE International Symposium on System Synthesis. Since then, it has been still the major yearly conference event worldwide focusing on all issues of hardware and software co-design. Since 2006, this important event has been organized under the direction of the Embedded System Week, also known as ES Week, with other major conferences such as EMSoft and CASES. In the early years, much focus had been put on tackling the problem of partitioning a given functional specification into hardware and software, hence a problem of bipartitioning. Here, two initial quite complementary approaches are worth highlighting. In the Volgin approach developed by Gupta in Stanford, California, the idea was to start with a hardware-only solution and to migrate as many tasks as possible to software while satisfying performance constraints with the goal to reduce design costs. The Codesign design system, developed simultaneously in Germany, took exactly the opposite point of departure by starting with a software-only partition of blocks with subsequent migration of tasks to hardware in order to satisfy performance constraints while trying to minimize the cost of the resulting hardware blocks. Nevertheless, these two early approaches stimulated a lot of work on subsequent investigations of partitioning approaches and architectural extensions. In the next few years, and until the early 2000s, not only the problem of hardware-software partitioning was elaborated on more and extended types of architectures, but also co-simulation came to birth, giving birth to an important area of research in the early validation of design decisions.
Today, we already live in a third generation of co-design technology, with cross-level design environments for the synthesis of complex electronic systems becoming slowly available. During the last decade, many important milestones of progress with respect to the initial findings have been achieved. The hardware complexity of many electronic embedded systems is not manifesting itself in SoC technology on a single chip, but also in communicating electronic devices, such as modern cars, and thus are the current modern issues. Imagine the complexity of a single vehicle that has 100 million codes coexisting and co-executing today. The complexity of testing and verifying these properties are so difficult. Thus, an obstacle has been and still is the lack of standards and ways to describe the integrated subsystems developed by potentially other companies and reuse these in order to respect reasonable time to market windows.
Now let's start part 2 of our lecture. We will talk about our focus topic in this lecture, which is design space exploration. Design space exploration, also known as DSE, refers to systematic analysis and pruning of unwanted design points based on parameters of interest. The driving factors for hardware is improved performance, improved efficiency, and reduced power density, while for the software section, it manages design complexity, reduces design cost, and sticks to design schedule. The complete picture is, however, way complicated. In the design of modern electronic systems, many trade-offs have to be made, and often between conflicting objects. Some factors argue for more software, while some argue for more hardware. Let's start with the arguments in favor for more hardware. Performance. The classic argument in favor of dedicated hardware design has been increased performance, and that can be described as more work done per clock cycle. This is still one of the major factors. Increased performance is obtained by specializing the architecture used to implement the application. This can be done, for example, by introducing dedicated hardware components to accelerate part of the application. Second part is energy efficiency. Almost every electronic consumer product today carries a battery. In the iPod, in the PDA, in mobile phones, in Bluetooth devices. Batteries have a limited energy storage. On the other hand, these consumer devices are used for similar services and applications as traditional high-performance personal computers. By moving part of the software of a design into fixed hardware, the energy efficiency of the overall application can be increased. The third part in favor of the hardware is the power density. The power dissipation of a circuit and the associated thermal profile is directly proportional to their clock frequency. In modern processors, the power density is at the limits of cost-effective cooling technology. Further improvement of performance can therefore not be achieved by increasing the clock frequency even more. Instead, there is a broad and fundamental shift occurring towards parallel computer architectures. At this moment, there is no dominant parallel computer architecture that has demonstrated to be effective for all applications. On the other hand, the argument for flexibility and thus for increasing the amount of on-chip software. Number 1. Design complexity. Modern electronic system designs are so complex that it's not a good idea to hard code all design decisions in fixed hardware. Instead, a common approach has been put to keep the implementation as flexible as possible, typically by using programmable processors that run software. Software and the flexibility it provides is then used as a mechanism to develop the application at a higher level of abstraction, as a mechanism to cope with future needs, and as a mechanism to resolve bugs. Thus, the flexibility of software is used to cope with the complexity of the design. The second thing, design cost. New chips are very expensive to design. As a result, hardware designers make chip programmable so that these chips can be reused over multiple products or product generations. The SoC is a good example of this trend. However, programmability can be found in many different forms other than embedded processors. Reconfigurable systems are based on the same idea of reusing. Third part is shrinking design schedules. Each new generation of technology tends to replace the older one more quickly. In addition, each of these new technologies is more complex compared to the previous generation. For a design engineer, this means that each new product generation brings more work, and that the work needs to be implemented in a shorter amount of time. Shrinking design schedules require engineering teams to work on multiple tasks at the same time. Hardware and software are developed concurrently. A software development team will start software development as soon as the characteristics of the hardware platform are established. even before an actual hardware prototype is available. In this diagram, under platform design space, we can see several programmable controllers, including the RISC processor, field programmable gate array, digital signal processor, application-specific instruction set processor, and application-specific integrated circuit. In case of the RISC processor, software is written in C, while the hardware is a general-purpose processor. In case of field programmable gate array, software is written in a hardware description language HDL, when the FPGA contained software processor will be using C. A digital signal processor, also known as DSP, uses a combination of C and assembly code for software. ASP can be specialized for a particular application domain. The software can be in C as well as hardware description of the processor extension. In case of the ASIC, the application is written in HDL. It is typically non-programmable, and the application and platform are merged to a single entity. In this image, the platform is organized from left to right according to flexibility. RISC and FPGA are able to support a broad range of applications, while ASIC is optimized to execute a single application. In between both of these, there's a third class of architectures called domain-specific platform, which are optimized to execute applications from a particular domain. The word flexibility here means how well is the platform adapted to different applications. Flexibility in some platforms is desired because it allows designers to make changes to the application after the platform is fabricated. An interesting and is very difficult way is how can we select a platform for a given specification, and how can we map an application into a selected platform. Firstly, from experience, and secondly, by using a design method. A design method is a systematic sequence of steps to convert a specification into an implementation, and usually is a canned sequence of design steps. For a chip on a mobile phone, the objectives could be minimizing the power consumption and chip area. For a field programmable gate array, the target for system implementation could be cost, could be the number of logic gates, flip-flops, and RAMs, used together with performance objectives to get the throughput and the clock rate of the synthesized system.
In our final slide, it is important to mention that new application domains demand ever-increasing adaptability and performance. The application and knowledge of hardware-software co-design techniques is a must for all those who want to keep up with the challenges of more and more complex electronic system designs. This does not only hold for SoC designers, but also for software and hardware engineers involved in the development of distributed systems. The wall of complexity. SoC technology will be already dominated by 100 to 1,000 core multiprocessing on a chip by 2020. Changes will affect the way companies design embedded software and new languages, and tool chains will need to emerge in order to cope with this enormous complexity. The wall of heterogeneity. In order to cope with the quest to also include the environment in the design of future cyber-physical systems, the heterogeneity will definitely continue to grow, as well in SoCs as in distributed systems of systems. The wall of dependability. Also, as has been shown, the correctness of future electronic embedded systems is definitely menaced by the imperfection of future transistor technology. Codesign will be mandatory to detect and compensate for such errors as well as aging effects in the future. There is no doubt that changes are required at the transistor level. The need for self-adaptivity. Due to the uncertainty of the environment and communication partners of complex interacting cyber-physical systems, runtime adaptivity will be a must for guaranteeing the efficiency of a system. The need for cross-layer co-verification. One huge part of the design time is already spent on the verification, either in a simulative way or using formal techniques. Researchers believe that with respect to the above threats, co-verification will finally require an increasing proportion of the design time in the future. The area of cross-layer co-verification reveals many unsolved problems that will require big research efforts in the future.
Thank you, and I hope that you found this lecture beneficial.